All right, so usually courses start with ciphers because, well, everybody thinks about ciphers when they think about cryptography and they think about encrypting confidentiality. I don't like starting with ciphers. I like starting with hashes because hash functions are just the nicest little tool. Like everything you do in cryptography, somewhere you have a hash function. The exceptions are tiny microcontrollers where you're so concerned about code size that you have to use one thing for everything. And there is no counterfactual for this, but I believe that if we restarted the cryptography today with what we know, and we just said, all right, we're starting fresh, new primitives and everything, I think we would build everything on top of sponges and hashes, and we would just have a single symmetric tool at the core of a hash, and then we build everything, encryption, authenticated encryption, we would just go up from there. You can even do signatures from hashes by doing particularly sparse Merkle trees. It's actually post-quantum. It's called SLH-DSA, the one they standardized. That's the one thing we're not going to talk about with hashes because that goes into asymmetric cryptography, so public and private keys. But if we stay on symmetric cryptography, which is where both sides have knowledge of a shared secret, a private key that they both know, hashes can do absolutely everything for you. Did we restart the recording? Yes. Okay. Did I start the recording? Yes. Okay. So hash function, very general concept of hash function. Message of arbitrary length, whatever number of bits, but if you specify your hashes as taking arbitrary number of bits, I would be upset. Specify them as taking arbitrary number of bytes, because generally we don't cut off things halfway a byte. Just never do that. So it's very annoying when you have to keep in mind whether something was specified over bits or bytes, and lengths might be themselves or 8 times themselves. So generally, arbitrary number of bytes, hash function, hash output. Hash output is a deterministic function, a deterministic pure function of the input, and it always has the same size, and it should be indistinguishable from a random string. So the theoretical formalism in the random oracle model, which is, according to some of the most purists, a weaker model, but truly is the model in which most theoretical proofs work, is that you could replace a hash function with a giant idealized table, where every time you ask for the hash of a value, the idealized table looks for that input in the table. If it finds it, it gives you that row in the table. If it doesn't, it makes a new entry in the table, which is a completely random value in the space of all of the values that the hash output can be. So a random set of bits of that length, because remember the entropy and randomness conversation of last week, adds that to the table and returns it. So every time you ask for the hash function of the same message, you get the same hash output. And if you ask for a different one, you get a completely random, completely uncorrelated value. That is the idealized model. It's the model you use when you're trying to prove things that use hashes as a component, and it's called the random oracle model. But in practice, hash functions, we really know how to do hash functions. We have not had a hash function break since SHA-1, which was designed in 90s, 80s, maybe. I think every hash function we've designed since 25 years ago has pretty much survived. I'll find and add to the course notes here a nice table that I didn't think of looking for earlier that shows over time the security of various hash functions. And you see like a few of them start getting, initial breaks pretty soon and then break. And then as you go down, they start going like green to the end, green to the end. We've figured out how to do hash functions. Hash functions are not a problem, and it's part of why they're in state. Just work. So we have these things, we know how to do them, that take large message and then hash it down into a small message where if you change even a single bit in the input, you get a completely random looking, completely uncorrelated hash output. You can build so many things with this. You can build a very rudimentary, for example, random number generator. Can you think about how to do it? You can make a reasonably good one with a very simple intuition. So you have a hash function that takes, you can put anything in it. And it doesn't really matter the order you put it in. As long as it's not the exact same, the output will be completely random and you will not be able to tell that they're the same unless you do the brute force work of trying all of the inputs to see it's the same, like a complete brute force. Can you think of how to generate an unlimited number of random numbers given a larger amount of entropy and a hash function? Go for it.
First thing, you keep a counter and just hash the counter.
So half of symmetric cryptography is add a counter, do it again. So you have the entropy, right? Just what happens if you hash entropy and then 1? You get a hash out, right? Those are random bytes. You can use them as random keys, as whatever you want. Don't actually use this as a key derivation function. We'll see later that there are better constructions for that. But point being, it looks random. And unless you know all of the entropy that went into the hash function, there is no way for you to know that that is entropy plus 1. And then you need more. So what do? Entropy, the same entropy, and then 2. That hash output, completely random, completely uncorrelated looking from the first one. And you can just keep going, basically forever. You can do the math on when like things start can start to look a little weird, but essentially it's attacking this as expensive as figuring out what the entropy was, which if it's 256 bits of entropy, or even just 128 bits of entropy, we don't count that high because there aren't that many nanoseconds in the history of the universe, so we're fine. So hash functions, you already can make a random number generator by just doing the simplest possible construction out of a hash function and a count, entropy and a count. Does that make sense? Okay, so a lot of the stuff we do looks like this. You take a thing that does a thing, like hashes that take arbitrary input and return a uniformly random output, and you build the thing you need, for example, a random number generator out of that. So brief step back for how do we make a hash? But first, does it make sense? Both what the hash does and why we can use it as a random number generator. Do ask me questions. Yes.
Is it like pseudo-random or like actually random? So I guess you cannot leave random stuff.
So that distinction of actually random and pseudo-random is something that comes up a lot when you're studying, like when you're very early in understanding cryptography, and essentially no professional cryptography engineer thinks in those terms. So what is actually random? Well, I guess if you take an atom of cesium and you measure, sure. There are physics definitions of actually random. Those don't really interest us much, except to the extent of collecting entropy. But entropy is kind of a small part of the job, because entropy is, once you've collected enough, the difference between something that looks random but it's pseudo-random because we use cryptography and actually random goes away. If I give you 256 bits of entropy, that entropy doesn't get compromised, which is a big asterisk. You know, that there are whole conversations about random number generators that take that into account. But if that entropy is not compromised, and then you do the counter thing with the hashes, it's computationally indistinguishable whether that is pseudo-random or actually random. So every time we say random, we actually essentially mean pseudo-random, unless we're talking about the actual entropy collected at the very base layer of it all, which we talked about last week, but it's the one that usually the operating system takes care of, and none of the cryptography engineering has to really think about. that there are maybe 1% of cryptography engineers ever think about the actual collection of entropy these days, because the operating system will just do it for you because the CPU has an instruction basically to ask for just random noise, and then they will put it in a hash pool and then hash things out and get or use ciphers and get out random pseudo-random looking bytes. So generally, when we think about random, we think about a distribution that is computationally indistinguishable from a uniformly random distribution. And that is good enough for us because all of what we're doing is computation. The only thing that's information theoretical is that one-time pad we discussed last week. But that actually doesn't do a lot of things we need. So there is no information theoretical entire crypto system. Everything is based on the computational assumption that you can't do 2 to the 128 anything. You can't do 2 to the 128 additions. You can do 2 to the 128 hash invocations to try them all. And since you can't, good. Then we can do cryptography. The entire field of cryptography would not exist if we didn't have that exponential that runs away from the attacker faster than it becomes expensive. Right. So that's how we can, that's what hashes do for us. Make sense? Cool. Taking a step back into how do we make a hash function. A hash function has the problem that you have a large message and then you want to compress down to a single thing. There are two main ways to do hash functions. There's Merkle-Damgard, which is, and there's sponges. Let's look at Merkle-Damgard because it's what is used by everything from MD 4, MD5, SHA-1, SHA-256, of which only SHA-256, SHA-2 is secure. Annoyingly enough, MD5 does not stand for Merkle-Damgard 5, but it stands for Message Digest 5, which, sure, fine. At least they didn't make an MD that's not made out of Merkle-Damgard, so it's fine. Or maybe they did before MD4, but that's like 80s. So these are different hash functions. They all do the same job. Like when you hear me say SHA-1, SHA-256, SHA-3, SHA-3 has a different construction, but they all do absolutely the same thing, which is large message, hash, small output that looks random. How Merkle-Damgard does it. Merkle-Damgard takes the message, splits it up into blocks, does some little padding at the end, which we'll talk about in a minute, and then uses a compression function. Again, a lot of cryptography is we have a bigger task, we have a smaller tool, we find a way to use the smaller tool to do the bigger task. So if we start at the top, we wanted a random number generator, but we had a hash. And so what we did is we put entropy plus a counter, kept running the hash, and we got a random number generator. Now we want a hash. How do we do it? With a compression function. So the compression function is a function that instead takes two inputs, one of size A and one of size B, and returns an output of size A. So one of the outputs is the same size as one of the inputs, and the other input is of a different size. The important thing is that this needs to be preimage and, well, it's ideally this compression function is preimage and collision resistant. What do these two terms mean? They're the same properties we want out of a hash. So if a hash is random, I described hashes to you, and this applies also to the compression function, which is inside the hash. But if I tell you, okay, give me, here is a hash output. Can you tell me what the input was? Yes or no? If I insist that you do, what is the best thing you can do to try to give me an input that hashes to that output?
Brute force all the possible.
Exactly, brute force. So you just brute force values until you find one that you can't actually find the one that I hashed because this is not a bijective function because the output space is smaller than the input space. So, that is called a first preimage attack. A second preimage attack is where I give you a message and I ask you to give me another message that has the same hash. Can you do that? Again, brute force. The only thing you can do is hash it and then hash random messages until you get one that has the same hash. Because here you don't control the message I gave. One of the messages is fixed, so the hash is fixed. The difference between first preimage and second preimage attacks is that in first preimage, I didn't give you the message. While in second preimage, I'm giving you the message, which is a little bit information more. If the hash function works well, second preimage and first preimage are just as hard. Because for both, you have to just try brute forcing random inputs until you find an output. If the function is a little broken, then maybe you can use the message to observe the internals of the hash function and try to do attacks that are based on that. If it diverges from the ideal. Otherwise, the attacks are the same. Different attack. If I ask you, give me two messages of your choice that have the same hash. Can you do that?
Okay, no, but it can be faster than the...
It's faster. It's faster because of the birthday paradox. The birthday paradox is the thing where if I ask if in a room of 30 people, there's one with a specific birthday, I have, the number of people over there. If I ask if any two have the same birthday, I have much higher probability, right? Every time you have a situation where the birthday paradox comes in general, the amount of work is the square root. So the number of bits of security is half. So if it takes 2 to the 256 to find the preimage of an ideal hash function, usually to find a collision, it's 2 to the 128. And in general, this will show up in all of the analysis you do. When there's some kind of birthday attack, probably the bit security is half of what it would be if there wasn't a birthday-based attack. And this is the only reason we ever go above 128 bits, because sometimes we want 128 bits of security. And since the attack can do birthday collisions, we need 256, 2 to 256 space to make sure that you don't get into a collision like that. And in general, you see this kind of a lot. Like every time you see a bound that's half, probably a birthday attack somewhere sneaking in there. Cool. Okay, so these are collision attack. Intuition for why a collision attack matters. Let's say that I am signing a contract. And instead of the contract on the page, I put the hash function of the contract. Like we take the contract as text, we hash it. We put the hash function, then I sign the paper. Let's ignore the signatures for now. But let's say I print out a hash output, and then I sign the piece of paper. If you can find a second preimage, you might tell people, oh, this Filippo signed a thing that I didn't actually sign. But can you think about how to use a collision to do the same thing? So a collision is when you can find two messages, so two contracts that have the same hash. You have control over the contract, so you can keep tweaking the language of the contract that you show me until it makes it easy for you to make the other version. And once we see how Merkle-Dallinger works, we'll see that you can usually do it in such a way that there's different parts, then there's a part that is the attack, and then the rest is of the contract is the same between the two contracts. So you can sometimes make it look normal. Like one of the two messages looks, yeah, a contract, words. And the other one also looks like words, but has different words. So if you have a collision attack in a hash, you can't use it in situations like this, where where some party will assume that there's only one version of the thing you picked. And this actually happens with certificates, but we'll get there. Okay, collisions, preimages. Now, random number generator out of a hash function. Hash function out of a collision, out of a compression function. Compression, how? That thing, Merkle-Dungan. So if we have a compression function that is collision resistant and second preimage resistant, that function that takes A and B and outputs a thing of the same size of A, we just chop up the message, chop up the input of the hash, and then run the function on each chunk. So we take the first chunk and fixed value. You'll see this a lot in symmetric cryptography. Oftentimes you can just fix a constant when you need an initial state. In some cases you can, and it has to be unpredictable or secret or uniformly random. Those are kind of bad primitives because people then mess them up because then they use a fixed one and they, but it's much nicer when you can just say, that's zero. You start with zero. And then you apply the compression function with message block 1. 0 and message block 1 gives you an output, which we're going to call H0, H1, H0 instead. And then you take the second block. You put H1 and the second message block into the compression factor, you get H2. Chunk, 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 chunk. And at the end, you take the thing. Finalization is not that much of a thing, actually, in Merkle-Dungan, which is kind of a problem. You just take the state that comes out of that function, that's your hash. Does it make sense how this turns a compression function, why is a compression function easier? Because the inputs have fixed size. So you can define them in terms of additions and multiplications and bit shifts and do stuff that you think will make it hard for the attacker to figure out a collision in it and a second upper image from it. But these are easier because they have 2 fixed size inputs, 1 fixed size output. And by applying it in a chunked way like this, you got a hash function. Does that make sense? One little tweak. At the end, you usually need to do some padding. Because what if your message is of 40 bytes and your compression function takes, I picked up a poor number. What if your input is 38 bytes and your compression function takes inputs, the ones at the top, the ones that are not the same size as the output, of 8 bytes. You're going to do the first 8, second 8, third 8, fourth 8, and then you're left with 6 bytes. You can't put 6 bytes in. So you need a well-defined scheme for how to pad those into a longer thing. And how that's usually done is that you do 2 things. One, you append the length of the whole thing. Because otherwise, you could do an easy attack where you could do where you could cut off a piece of the message. And I mean, it's not that easy, but it will make a lot of things easier to do in the attack if you don't also put into the function the length. And then you just put a 1 bit and then zeros until the end. It doesn't have to be this way. The concept we're looking for when you were doing things like this, like padding, is parsability. So we want it to be rejected. If you can take the thing that I actually put as the message at the top and always, regardless of, recover what the original message was, it means that there are not 2 messages that will come out to the same thing. Because otherwise you could not go back. So how do you parse this scheme that I just said? Well, we said it's message, length of as 2 bytes or something like that. I don't remember. Length 1, 0, 0, 0, 0, 0. So if you want to parse it, you go from the back. You remove all the zeros until you find a 1. You remove the 1. You take the next 2 bytes or whatever. That's your length. And then the rest is the message. So if you can parse, then it's domain separated. And there is not 2 inputs that map to the same output if you can go back by parsing. This feels simple and intuitive. So much stuff breaks because somebody like puts together things in a way that doesn't work like this. For example, what do you do if you want to hash two words? If you just concatenate them, you did not create a parsable sequence because you don't know where one starts and one ends. And so now you have collisions where two different pairs of words can come out to the same hash if you hash them that way. If instead you put a space between them, that's already sufficient. Because to parse them, you just look for the space and cut there. And the two different words that will come out to different outputs. This happens all the damn time because this is simple enough that it's not something that you rely on an existing construction for. And developers are like, it's just two words. The hash function was made by the cryptographers, but I can just use the hash function to hash two words. I'll just concatenate them. And I'm saying words, but usually it's different things like, I don't know, a database row followed by a file. And then you can do fun things like actually the other way around, a file and then a database row. You can do fun things where if you make the file have a database row at the end, it can look like actually the file is shorter and the database row starts sooner. And now you can maybe convince a system that the database row said something different because if this stuff sounds fun, there's Angie Albertini does this fantastic research on this sort of stuff where he takes different file formats and creates files that are at the same time a valid zip, but also a valid JPG, but also a valid, and they're valid in many different formats because each of them interprets it a little differently. And yeah, it's great. Andrew also worked at attacking one of the hash functions, SHA-1, because some of the work has this shape when you're trying to then actually use the attack. And he opened a bottle of green chartreuse when they finally cracked it. And I'm very happy to have drank the last sip from that bottle a few months later at a party. It was nice. Cool. Okay, so Merkle-Darmstadt. Makes sense? Merkle-Darmstadt still has a weakness, which is not captured by the random oracle model. It's called length extension. So imagine that you hash a message that is just one block. And then how do you do it? You call the compression function once, right? And then you call it another time with the length and the padding, which we just discussed. And then you get an output, right? There is nothing in the scheme that distinguishes that output as the hash, which you're going to publish, give people or something, from the intermediate value that comes out here. So you can just take that hash function of hashing a one block and length padding, put it back into the algorithm here, and keep hashing. And that breaks neither collision nor pre-image because the hash function will be different, the hash output will be different. But it does break the random oracle model because it means that if I give you the hash of one block, you can give me back the hash of that block followed by some garbage, which is the length and the padding, plus whatever you want, because you just keep hashing whatever you want into it. And you don't have to know that first block. If you know the first block, you can always do this. You can just run the algorithm yourself. But the point is that you might not know part of it. For example, if I try to authenticate something by saying, well, I have a hash function, just like I'm getting ahead of myself, and this was the next 45 minutes. But keep in mind that this property of Merkle-Darmstadt. All right. We keep going lower. We wanted a random number generator. We made it out of a hash. We wanted a hash. We made it out of a compression function. We want a compression function. What do we make it out of? A cipher. So a cipher is a different function. It's a function that instead takes is a permutation that takes an input of a certain size, a key, and produces an output of the same size. And then with the same key, you can go back. It's a keyed permutation. So each key selects a family of it's a family of permutations where each key selects one of those permutations. And with that key, the permutation is always the same. How do you make? We have many of those because that's the first thing we started with in cryptography. This is all very path dependent. This is, again, not how I would build cryptography if I were to build it today, not how anybody would build it if it were built today. But since we started with ciphers, we had a cipher, and so we kept building stuff on top of it. And so out of cipher, we made a compression function. Out of compression function, we made a hash. Out of hash, we made a merge. Cool. So that's how it's used. So you take the cipher, you make the input the previous state of the hash. You make the output the next state of the hash. You make the message the key, which is kind of weird, but it makes sense because remember, of the two inputs, one has to be the same size of the output. The other one can be of a different size. Same with ciphers. With ciphers, the plaintext and the ciphertext are the same size. So they have to be the two states. While the message has to come in the other side of the little function. Why the XOR? Because you could trivially attack Merkle-Damgard if it didn't do that step inside. So now we're looking inside the box F. If the box F didn't have this XOR operation here, where you take the input and XOR it with the output of the cipher, you could rewind by decrypting. Remember, these are permutations where knowing the key, you can go from plaintext to ciphertext or from ciphertext to plaintext. So you could go back. By knowing the message, you could trivially invert it and figure out the previous state, which you're not supposed to be able to do because that lets you then just search a smaller space of the previous one, or even a much smaller. Imagine you know almost everything except a few bits. Well, that's still possible. Anyway, this is a trick that is you see a lot of times. When you have something that is completely public, like a permutation like that, but you want the output not to be invertible, you take one of the inputs, you XOR it with the output, and that's your new output. Yeah, we do that all the time. Also build string ciphers. We're going to see that tomorrow. Okay, we've touched rock bottom. Inside that E is stuff. There's no more structure at that point. Like ciphers are kind of made up. There are certain operations that we think make them harder to break. We know that they have to be non-linear because if they're linear, you can do just linear math to them and then invert them. But yeah, the stuff inside there, we know there's a concept of differential cryptanalysis that you can apply to when you find linearities to try to follow some of the bits from the input to the output and how they influence each other. But all of that stuff is based on what we figured out so far. There is no theoretical proof for what's inside that little box there. But that is symmetric cryptography. We take the smallest thing at the bottom there, which is usually a permutation. And then out of that permutation, we build on top with provable constructions all the way up. And here we took cipher, compression function, hash, random number generator, and you see you can make all sorts of stuff with hashes. Like after the break, we just look at all the things you can make with hashes. I keep saying this is not how we make it today. Because sponges are great. Right, so you have this tool, you have this permutation. And what is a secure permutation? A secure permutation is one where the output looks, each output looks random, uniformly random, unless, and even if you change a single bit in the input, everything in the output changes. Those are secure random permutations. Just like the hashes, where we could imagine them as a little table, the idealized table, permutations are the same thing. Permutation, ignore the key. The key selects one permutation from a family of permutations, but a single secure permutation is a thing where if you change a single bit in the input, everything in the output changes, and by looking at two outputs, you can't tell that they're from related inputs except by inverting the permutation. Permutations are invertible. They don't have a key because, again, that's already one step up in the abstraction concept. The key selects one of the permutations from the family. If you have a permutation, you can do a much better hash design, which is this. You start at 0, and then you split that fixed amount of state. And the nice thing about this is that it doesn't have any function that takes two inputs, like a cipher with the key and the message. All of this instead just uses a single permutation, not a family of permutations. And you split it into two things, the rate and the capacity. Then you again chunk the message up. We are always doing that. Well, you take the message and you split it into P0, P1, P2, at fixed size. And then for each of them, you XOR it with the rate part of the state, and then you run the permutation. So you start with zeros and the message, first chunk of the message at the top, and then permutation. So what the permutation does is that it diffuses all of the bits of that part of the message into all of these bits. Now, all of these bits depend randomly on all of the bits over here. Then you XOR again with the second chunk, and you permute, and you keep doing it. And then at the end, you say, okay, I am done putting stuff in. I want to start pulling stuff out. So what you do is you take the output, and the rate starts becoming your output instead of your where you XOR the input. And you can go as long as you want. That's the nice thing about sponges. They don't have a fixed size output. With Merkle-Damgard, we had a fixed state, and that state was the hash. So we couldn't extend it. With sponges, we can just keep going. So we can absorb for as long as we want, and then we can squeeze for as long as we want. What is the security intuition of a sponge? When you're squeezing, you reveal a piece of your state. And when you're absorbing, you let the attacker control a piece of your state. But there's a piece of the state that the attacker never sees. The rate is the one that gets either controlled or revealed. The capacity is the one that instead is your reservoir of unpredictability, your reservoir of randomness. And since every time you run the permutation, you are making all of these bits depend on all of these bits. If the attacker doesn't know these, it can't predict what will happen to the entire thing. And by just knowing these, without knowing these, it can't invert the permutation. Because to invert the permutation, you need to know the entire output state. Otherwise, they would be correlated, two different states that start with the same bits, for example. So now we give a number to C, like how many bits is this, and we can calculate the security of the hash based on that. And the security of the hash is basically C divided by 2. So if you keep 256 bits of capacity, you're golden. And if it's divided by 2, that's probably because the attacker is? It's a birthday attack. And why is the birthday attack? Because the attack succeeds when any of these states matches one that the attacker can generate. If the attacker can get a sequence that matches like the capacity that's here, they can take the different path to arrive there, so have a different P0 and P1, and then from here on, it will come out the same because they matched it. And so it's a birthday attack, both for collisions, which is always a birthday attack, and for second preimages. which is a lot less intuitive, and for secondary images is a type bound. For first-pair images, sponges are actually a little stronger than that, and it took until 2025 to find a type bound for that. It's a fun paper, but nobody cares about first-pair images. Like, we care about the hash being collision resistant and all pre-image resistant. So essentially, we need this to be at least 256 bits. Pretty much. The last thing is that you also need to squeeze out enough bits to have the security you need, because if you squeeze out 10 bits, you're going to have 10 bits of pre-image resistance and 5 bits of collision resistance. So generally, you squeeze out 256 bits, 125 bits of collision resistance, and moving on. So what makes sense is having a hash function where this is 256, that is 256. It would be nice to have that. We don't have that because, like, the previous one had 256 bits of collision of pre-image resistance and 125 bits of collision resistance because it was a Merkle-Damgard with 256 bits outputs. So you had to do 2 to 256 to find a pre-image, but and 128 to find a collision. And since people wanted to have a drop-in replacement for that, SHA-3 has parameters such that when you use it, SHA-3 256 has the same security as SHA-2 256, which is annoying because it makes it slower, because we have to make this bigger, which makes this smaller, which means we have to make smaller pieces of the message, which means we need to run the permutation more often, which makes it slower, which means that people don't use it. Reality is. And I think we are at break. Does this make sense? Want to ask questions before the break?
So this is just a design choice. Last thing you said. So we could have had a different choice, and
we could have had we could have had a faster SHA-3 256, which had 128 bits of collision resistance because the output was 256 and capacity was 256. And could have had a pre-image resistance of also 128, which is secure. But people were like, but no, but that would be less secure than the previous thing. Again, there's nothing that can do 128 bits. But there's a whole thing built these days around security levels. Like some confidential things must be protected with 128 bits of security, secret with 192, top secret with 256. It's bullshit. It's just a remnant of when there was actually a lot more cost to doing things securely. So you had to take trade-offs. And like in the battlefield, you would have to be like, we're going to use this quicker and cheaper thing because, we don't have the time to do the more secure thing. But these days, the lowest security thing is secure. We could just have the lowest security thing and, say CPU, but we don't. And we argue endlessly about it. But yeah. It is what it is. A lot of the top-level decisions are path-dependent social decisions. Yes. And so in general, few people use SHA-3, the sponges. They keep using SHA-2, which is the Merkle-Damgard one. Also because CPUs have like actual silicon to do SHA-2, and they don't have actual silicon to do SHA-3 except the very, very newer processors. So SHA-2 is still faster.
Yeah.
Yeah.
So, based on the last thing you said, this is an operation that is done very often on a computer.
Very often. Oh yeah, all the time. All the damn time. Hashes that have everything that's hashed. Sometimes also non-security things hash stuff because it's nice to know that you got the same thing. A lot of things to upload a file will usually do a hash just because it's cheap and you want to make sure that no bits got flipped in transit. Which in theory, the underlying layers of the connection should also have checksums that prevent that. But the end-to-end principle tells you that oftentimes you're better off just checking at the very ends of the process if the file is the same and then you just hash. Everything's getting hashed all the damn time. And all all the packets of words I am saying are probably getting hashed a dozen times. Because they're going to Zoom's recording, because they're going through the TLS connection that is going from Zoom to the Zoom servers. Like each time it gets hashed. That is hashing. These are very fast functions. Okay, so we built a hash. What do we build out of it? Well, you try building this. We share a key, and we're trying to make sure that a message that we exchange does not get tampered with. So, I type a message, and then I want to do something with hashes. I have a secret key. It's 128 bits, so it's secure. You know the same 128 bits, and you know everything about the procedure. But I have to save this message on a USB drive that I'm going to give to him, and he will bring it to you. He can do anything to that message. You want to make sure that that message doesn't get tampered with. You have a hash function and a shared key. Go.
You just concatenate them before the hash, and then you attach the hash to the hard drive, so my friend should check that the hash is the same.
Excellent. That's called a key prefix. And it fails precisely because of the thing I was telling you about, the Merkle-Damgard thing.
It's important to know the question. Can you repeat briefly?
Oh, for the recording. Yes. So the suggestion was you concatenate them. You take the key, then the message, you hash them all together. You put the hash onto the USB drive together with the message, and the other side has to run the hash again with the key, which was not on the USB drive, and check that it comes out to the same thing. Yes?
Maybe you can also add some bytes. Like you decided to add some bytes and then you will hash them.
You add some bytes at the end?
Yeah, you have I don't know, 11100, and then you the hash.
Okay, so the suggestion is you add something at the end and you also hash that. That also breaks because the suffix keeps breaking. So example from Wikipedia, but all hash extensions are the same. So that's no. So here is the original message, the honest one, and this is the hash. It calls it signature, but it's doing exactly what you're talking about. These things technically are called authentication codes, like as the theoretical category, because they are things you do authentication of the message with. And generally, we talk about authentication codes when they're symmetrical and signatures when they use asymmetric cryptography. But a message authentication code is also a symmetric signature. So sometimes you'll see them called signature. Anyway, just because it's on the screen. So you have this message, and you actually want this message to arrive to the other side. So what do? You hash this message. And how do you hash this message if you don't know the key prefix? You cut, you know that the hash function up to here, the intermediate hash state up to there, is the one, is the hash output if you're using Merkle-Damgard and using SHA-2. So instead you say, oh yeah, my new message is this. So think about the intermediate states of Merkle-Damgard, the thing that hashes one chunk at a time into the intermediate state. When you get here, the intermediate state will be the same as when you're done hashing this message. Because at the end, we add the 1 byte, the 1 bit, the zeros, and then the 2 bytes of length. And if you added any bytes at the end, these would end up here. And you could do the same attack. Now, you're also relying on a bit on how the message is going to get read, because this message will look weird to a human, but a computer is very likely to look at this message and say, Okay, so count 10, latitude 37, user ID 1, longitude 119, waffle, egg 800000228, waffle, leave. And the second one overrides the first one. Boom. So now this message that you know the hash of, because you can compute it by putting the output of the previous hash into the intermediate state here and then continuing the hashing, even if you don't know what's in the prefix here, comes out to mean the same thing as this, or even without this part. Ooh. Should move it up. So putting the key at the beginning works in the random oracle model as a key prefix. It doesn't work in practice because many hashes are Merkle-Damgard. Does it work with sponges? Yes, of course it works with sponges. Sponges are better than damage. But no, we don't have sponges, so we have to come up with shit. So how do we design a secure one? Do you have ideas?
Without changing the hash.
We keep using the hash. Yes, we keep using SHA-2. I mean, the secure one with sponges is exactly what you described. If you have sponges, you can do exactly what you said, and that's a secure message authentication code. You can take the key, the rest, done. There's actually a recent paper that tells us that putting the key at the end is secure, but it took until like 2 years ago to get a proof of that. So, sketchy. Not super safe. And also that only works if the key always has the same size, because otherwise you have the problem we were talking about earlier, that if you don't know what the length of one thing is and the length of the other one is, then it's not parsable where one ends and one starts. This is in general always true when you're concatenating things. You either concatenate many fixed size things and one 0 or 1 variable length thing, or you have to come up with an actual scheme for the length of a thing. So you have to be like hash first the length of the first thing, then the first thing, then the length of the second thing, then the second thing. And anyway, key suffix might work, not recommended. But this cryptography, we can just keep building things on top of things. We have a hash, we want a message authentication code, a MAC. How do we build a MAC out of a hash? HMAC. HMAC might be the most versatile function because it's a double PRF. So it's a pseudo-random function with 2 inputs. One is the key, the other is the message, and the output is indistinguishable from random, and PRFs are just very, very, very useful. There's a whole thing around PRFs versus PRPs, which we're going to talk about tomorrow. PRP, pseudo-random permutation, the permutations that we build things out of at the very bottom. PRF is a pseudo-random function, which instead is, for example, a hash in the random oracle model, where you can't go back. While PRP, you can go back. And notice how we keep just building larger versions of the same stuff, just out of smaller pieces. We started with a PRP at the very bottom. We kept building up, and now we have a PRF because this is a PRF anyway. But this is a variable length PRF, while the thing we started with was a tiny fixed length PRP. Okay, does this make sense? The stuff at the top is just some mangling to do domain separation to get different starts from a single key. So you have a single key, you XOR it with those 2 values, which are fixed. iPad and OPAD are just, I think one of them is all zeros, there is all ones, the other one is all 8s, something like that, like, doesn't matter. So you XOR them, then you do exactly what the thing we were doing earlier. So the first pass is just prefix, key, suffix, message, hash. And then you do it again. That's it. You take the other tablet key, And why do we have them different? Because this way you can't swap these out in an attack. You can't take this and say it's the I keypad for the hash. So the starts are different. This might not actually lead to an attack if they're the same, but it makes it much easier to prove that it's correct. You will see there's a bunch. Sometimes you do things in a slightly different way because it costs you nothing and makes it much easier to reason about the security. So you just do it twice. Prefix, message, hash. Prefix, the hash that came out from the first time, hash again. Done. HMAC. Everything does HMAC. HMAC is so good. You can HMAC everything. HMAC never breaks. HMAC, all of the extra so remember how I told you, what is a secure hash function? It's a function that where you can't find preimages and you can't find collisions. And then I was like, except now you can do length extensions, even if it's a secure hash function, because actually you wanted an extra property out of it. And this happens a lot. You need to know what the properties of the thing actually are. And sometimes the intuitive properties are not there if they're not in the list of actual properties. It's no second preimages, no collisions. Those are the actual properties of hashes. No length extension, not actually a property of hashes. A property of sponges, not a property of Merkle-Damgard. Both secure hash functions, not both secure if you do the prefixing. It's much nicer when a primitive has more security properties. Although there are people that will tell you, but no, that will make people think that all of the hashes have that property, and then they will shoot their foot off when they swap it out. I don't believe in that. Just make things safer and try to move the world towards the safer things. And then maybe somebody will mistakenly rely on a property that is not guaranteed by hash, but if it's using a sponge, it will be safe. Same HMAC. HMAC has all of the properties. MACs are not even supposed to be indistinguishable from random. The only thing that MAC has to do is Giovanni can't figure it out, can figure out a new MAC for a different message. That's the only property of MACs, because that's what we're using it for. Remember the USB drive that Giovanni is carrying. So the only property of MACs is Giovanni cannot come up with a new tuple of message MAC, which is not the one I showed them and that you will accept. That is the only property of MACs. They can start with 0000 and then have more stuff, and that would be valid. And so, for example, they will not be random. A MAC doesn't have to be random. Except HMAC is everything. HMAC is random. HMAC is a double PRF asterisk, something about the length of the key. HMAC has all the things. I love HMAC. This is an HMAC appreciation session. Cool. Questions? No questions? All right. Cool. We built a MAC. What is another thing we might want to build out of existing primitives? Key derivation function. What is a key derivation function? You have a key. You want 3 keys to use with 3 different things. Can you think of a way to do it?
Hash them.
You can hash them with a counter. That works, but what is the problem of key derivation functions? What if somebody does something very stupid and uses the same key both as the input to a key derivation function and as the input to a random number generator? And we just finished designing a random number generator. What was the random number generator? Same. And maybe those random numbers, you just hand them out as lottery numbers results. What happens to your keys over there?
Someone can figure it out.
Yeah, they just look at the numbers that come out of the lottery, and those numbers are the key, because you did key derivation and used the key in a different protocol, and that ended up sharing. Now, this sounds like, it's not going to happen that often. No, it happens doesn't happen that often these days because I think we have drilled into people's skulls that you cannot use the same key for two different things. You have to put a KDF in the middle. Like, it's fine if you have a key, do a key derivation function, get two keys, and use one for encryption and one for lottery numbers. Totally fine. You need to not use a key both for the key derivation function and for something else. That sometimes still happens. So what is a secure key derivation function? A secure key derivation function is one where this is much less likely to happen, and one where people that have the other keys can figure out each other's keys, given one key, you can figure out the other key that was derived from the same KDF, and they are all uniformly random, and they carry over all of the entropy, but those are intuitive. The non-intuitive one was that. And how do we do that? HKDF, because we keep building things on top. And what do we make HKDF out of? HMAC, because HMAC can do everything. So how do you do key expansion, which is the same thing as key derivation? Because if you can expand a key into a longer key, and then just chop it up and say this is the first key, this is the second key, this is the third key. How do we do that? It is pretty much hashing a counter, except you usually do it by hashing a sequence, which is HMAC, a sequence where one input is the key, and the other input is usually a sequence of a counter and some context. So, for example, this is the key derivation function of protocol foo for purpose bar on behalf of user 10, and you put all of those in there. Then you put user's 10 key in as the key, and you run HMAC on a counter, and then what comes out, that's the key derivation function. Yeah, so we went. Want a key derivation function, we're going to use HMAC. Want HMAC, we're going to use a hash. Want a hash, we're going to use a compression function. With a compression function, we're going to use a block cipher, and that's the problem. I'm a big fan of this little tower, but also sponges, because you don't need HKDF and HMAC if you have sponges. If you have sponges, instead, what you do is you just put in like if you want MAC, it's called KMAC, and this is called HMAC. That's called KMAC because it uses Ketchup, which is the original name of Chatri, the sponge construction. Anyway, how you do it is that back to sponges. In the first rateful, you put what you're going to do with it. So you put, I am doing KMAC, and I'm doing it on behalf of this user, etc., etc. Then in the second one, you put the key and nothing else. Why nothing else? Like, even if there's more space, why don't you start putting the message in? Because this way you can run these three permutations and just keep it over there. And if you want to authenticate multiple messages, you can pre-compute this, because this part is always the same. If the user is always the same and you're always using KMAC and the key is always the same, even if the messages change, which you're going to sponge absorb here, you can pre-compute this way. And also it helps some with side channel attacks. It's a little easier for the attacker to measure your power differentials and do weird things to your computer to figure out what these bits are if the attacker can control these bits. If it can't, it's hard. Side channels are a game of cat and mouse. None of this is, what's the word, rigorous, but essentially when people who do hardware side channels tells us, oh, that would make things a little harder, we do it, because that's making it hard. And yeah, that's it. No HMAC, no anything. That works. And that's called KMAC. Yeah. The other nice thing you can build out of sponges are XOFs, extendable output functions, which are essentially the known keyed version of HKDF. Sometimes you use HKDF simply because it can produce an arbitrary amount of bytes, not arbitrary, the counter runs out. Because you keep hashing new counters and you can get a large. But XOF can do that spontaneously because remember, we can keep squeezing. A hash has a single output size, and HMAC has a single output size, which is the size of the output of the hash. But XOFs simply don't cut off here. Usually when you're doing when you're using a sponge as hash, you just stop squeezing after you got the output size you want. You can just keep going. And not only you can just keep going and build that expandable output function, you can build a cipher out of it. This is a bit of preview of tomorrow. But can you imagine how to build a cipher out of a sponge?
Cipher is a function that takes Ian plain text and cipher.
Correct. So earlier we solved the problem of I want to put the message on the USB drive and I want Giovanni not to be able to tamper with it. And to do that, we're gonna put, we said, some domain separation purpose stuff here, the key here, the message here, and then we're gonna take this and this, put it into the USB drive, and Giovanni can't figure out that value for a different message because it doesn't know what to put here. Cool, cool. So we've solved authentication. Now we want to also make the message secret. How do we do that? Let's say for now that we have another key for secrets, but we could also do a key derivation function where we put the key there, and then we take this key to put back in there for another instance, and that key to do something else, which is the encryption. How do we do the encryption? We have the tools to do it.
You should also be invertible, right?
Correct.
You want to be
Correct.
We just use one-time padding with the output.
Yes, exactly. You've just invented a stream cipher. Stream cipher. You just put parameters, the key, and then nothing else. And then you squeeze until you have as many bits here as there are in the message. Then you do XOR between those bits and the message. Done. A stream cipher is just a concept that you find some way to generate a pseudo-random long sequence of random bits, and then you XOR them. Stream ciphers are essentially expanded one-time pad. You have a way to generate a one-time pad from a smaller key. You do it, and then you do one-time pad. You do both that and the authentication, you have a secure authenticated encryption scheme, which is getting ahead tomorrow, but sponges.
Can you do this only with sponges, or is there a way to use the other Merkle?
So it's a hash-based cipher. It's going to be horribly slow because every time you have to you would have to use HKDF, for example, with a much bigger counter, because HKDF, the counter goes up to 256, 255. So the message can be very long. You can do that by just redesigning it a little bit. It's just it's going to be super slow because instead of just doing the permutation, which can be extremely fast, you have to do this entire bunch of stuff where each of these arrows is all of Merkle-Damgard. And yeah, that's kind of slow. This is not particularly fast either. We have faster ciphers, but yeah, close enough. Although the fast stream ciphers don't look very different from this, which is why I'm telling you this stuff is path dependent. We came up with the fast stream ciphers that we're going to see tomorrow, approximately at the same time as in parallel somebody was coming up with sponges. So ridiculously, there's a hash function called Blake2, which takes the permutation from a stream cipher, which is just a permutation like this, modifies it not at the level of building around it, but like actually modifies it to turn it into a block cipher, to put it back into Merkle-Damgard, to use Merkle-Damgard. And they did that because they wanted to derive a hash function from that stream cipher. That makes no sense to me. And one day I want to find the author of that at a conference and confirm that if they did it today, after seeing sponges become popular, they would instead just take the permutation, not modify it, to also take a key input, which then in Merkle-Damgard you reuse for the message chunk, and go all the way around to then do Merkle-Damgard, and that instead just taken the permutation, chunk it into a sponge and move on. But path dependence, that's just not how reality happens, so that's not what we get. It's probably still secure, and it's still fast, but it would be nicer. There is one ecosystem of symmetric encryption built out of a single permutation, which is called ASCON. It was designed because, I think it was designed because somebody was as annoyed as I am by the fact that we weren't doing everything with sponges and wanted an excuse for it. But the official reason is that they wanted to build lightweight cryptography. So cryptography that works for very tiny microcontrollers where you don't have a lot of code space. And if you don't have a lot of code space, you don't want to bring in a block cipher for the hash, the Merkle-Damgard, the message authentication code, the cipher. It's nice to bring in just the implementation of this and use it for everything, right? And so they made ASCON, and ASCON is nice. You can do everything with ASCON. I think they're standardizing now ASCON-based encryption that does that thing we just discussed, like use it once for authentication, then once for to get the one-time pad for confidentiality and so on. But we can talk about those tomorrow, but does this make sense?
There's time. So about the cipher, what you said is just, so you compute you give the key as input to the sponge.
Yeah.
You use you squeeze out as many bits as needed, and you just send the XOR between this and your message, right?
Correct.
Okay. So you will always use from the same key. You will always use the same one type of the.
Oh, sorry. Yes. I mean, tomorrow we also talk about nonces and so on. Yeah, no. So that's a problem. That means you can only use the key once because if you use it again, you're XORing with the same stuff. So instead, what you do is you take a random value every time you do this. You stick it in there, and now the output is different every time. And then you do all of the math to make sure that the birthday band of taking random values and putting them in there, and the birthday band of the capacity and all of that doesn't come out to collisions, because a collision would mean that you again XOR with the same stuff. But that math is just tediously figuring out the probability of a collision by keeping track of all the bounds. But no, so what
you send a random number.
And you send the random number alongside them. So the end output of authenticated encryption system usually is a random number, the XOR of the message with the stream that was generated from the key and the random number, and then the message authentication code. Tomorrow we're going to see actually how they look like in practice, but if there was no path dependency, I won't make this. But there was path dependency, so we're going to see how there's a different way to take a block cipher and turn it into a stream, which does not involve, because we had block ciphers before we were even thinking about them in terms of permutations. So we figured the first thing we developed was just the block cipher, and so we use block ciphers for everything. And anyway, permutations of this. I keep saying this, I realize. All right, let me look at whether I skipped something. Hash extensions we talked about. I'm going to put in the notes the link to an exercise with hash extension if you want to try it. It like describes a little setting in which you can actually try implementing such an attack. We talked about the capacity parameter waste of the official parameters and how I'm upset about those. Oh, there is one neat construction made out of Merkle-Vanguard, which is still protected from hash extension. One thing you can do is make the state of that large, like 512 bits, and then at the end, chop off 256 of those bits and call that your hash. Can you think why this doesn't allow length extension? Because to plug it back in, you're missing the second half. This is called SHA-512/256. It's good. Nobody uses it. It has a longer name. I'm kidding. Only 30% kidding. I think it's a trading part. It has a confusing name because it has two numbers in it, so people don't use it. It's actually, I mean, no, there's also the fact that it was slower on older CPUs. On newer CPUs, it's actually faster because it essentially works the same as SHA-256, SHA-512, but uses 64-bit registers. Our CPUs now have 64-bit registers, so do operations on 64-bit numbers. CPUs back then did operations on 32-bit numbers, and if you wanted to do an operation on a 64-bit number, you had to use two registers and carry the one and do stuff like that. That was slower. So these days, it's actually the other way around. It's faster to use SHA-512/256 than it is to use SHA-256. Except for a while, there was special silicon in chips to do SHA-256, but not SHA-512. And so even with the newer processors, we went back to being faster using SHA-256, which, however, had length extension attacks. And so it's trade-offs all the way down. And if we just had, if we only put in silicon the permutation to do the sponge, none of this would have happened. So yeah, SHA-512/256 is actually a very good solution for when you need a known length extension hash and you have reasonably recent hardware such that you have the SHA-512 instructions, but not the SHA-3 instructions, but it's very much a know your feet kind of situation. And yeah, the list of trade-offs then gets longer because then does your library implement it and expose it and that. There's also usually how the compression function is implemented. So how the tiny cipher that's inside there is implemented is by doing many times a certain operation, like shuffling the bits, or like reordering or rotating them or adding them. And remember that this has to be invertible because it's a permutation, which is harder than just mixing things. So usually you do an even smaller thing, which is the round. Keep going smaller. And you do many rounds of a thing. And usually, like 2 rounds of the thing is broken. You can do collisions, you can do pre-images, and 10 rounds of the thing is fine. And how we pick how many rounds to do? So there's this good paper by the same author as the book called Too Much Cryptography, which makes the argument that all of this stuff has too many rounds. And this also includes sponges, because how you do the permutation is, you guessed it, you have a round function and you do it many times until the stuff is mixed enough that you can't tell why a bit came out that way. the team that made Ketchup was kind of upset that they made this very good round that turned into this very good permutation that even with a reasonably fewer rounds, and then made this very nice sponge that was very fast. If only you made the rate a little bigger, and then NIST did not make the rate bigger, and so SHA-3 is slow, and so nobody uses it. They're a little salty about it. And so they designed a thing called Kangaroo 12, which is Ketchup with 12 rounds instead of whatever SHA-3 uses, and the better capacities. And it's a thing and nobody uses. Because it's not standard, so you can't get it certified by NIST if you use that. And there's a limit to how many things we can implement in a library. Like we can't tell you, oh yeah, you want a hash function? Here is 15 options, pick. So generally we want to tell you, yeah, use that one. And I would let you use a thing that has 128 bits of security because nobody can count to 128 bits, etc., etc. But NIST does not standardize it. So if I make you use that, then you need to use a different one when you want to use the standard stuff that is accepted by NIST. And then, you know.
So you are also Monday. So you can start sneaking the things that you think are best.
He's saying you're an open source maintainer, so you can start pushing for the things you think are best. I mean, I have two, there's a tension here. On one hand, I want to get in the things I like. On the other hand, I don't want to maintain 15 things because then I have to make them all fast. And making them fast can mean like go very like in the very details and figure out that if I do this addition first and then this, the CPU will schedule things in a different way. And like that's so much work and I have to do it for each of these things. So yes, there's a tension. And generally what I've started doing is I started working on specifications and trying to get a specification down, which I think does the good things, get everybody on board on that specification so that then I implement that. And I use some of the weight of the Go project to say, this is a good spec, we should all use this instead of, but just adding a thing I like, which nobody else implements, will only add one thing to the things I have to maintain. Like I will have to implement both the thing I don't like and the thing I like, which is certainly more work than just the thing I don't like, which would be also more work than only the thing I like, but I don't get to. So. Yeah, and this is an argument I've made about other things where I said things like, yeah, sure, that signature algorithm is a little better, but it uses a completely different elliptic curve from the one I have to implement anyway for this thing over here. So my time is finite. True, I can make that one in theory a little more secure. It's a little easier to implement. It's a little faster. But if I take all of the time I would spend getting that to that point, and apply it to this, I can probably squeeze more out of this one that I have to carry anyway. And so why would I? Yeah. And then quantum computers came and none of the elliptic curves matter anymore. Also, I spent the last 3 days dealing with the response to an article I wrote about, so quantum computers becoming, yeah, sorry. Part of why I wasn't responding was that I was like, oh, okay, lots of people have opinions after writing that. And I'm going to put the article in the notes if you're curious, but it's essentially talking to my colleagues saying, so we were hoping we had more time. We might not. We might, but we might not. Okay. We talked about KMAC, we talked about KEF, collisions, tuple hash. Sure, why not? We have 5 minutes. We can talk about that last. We talked about how it's hard to do that domain separation thing. Right, that the thing where you should just concatenate, you don't know where a thing starts and the other ends, and so you risk hashing two pairs to the same value. And we talked about how, in general, it's a thing that developers think they can reinvent, so they reinvent it. And there's the whole rabbit hole of canonicalization, which is related, but let's not get into it. But there is actually a standard function for hashing a sequence of things, a tuple, and it's called tuple hash. And it's specified on top of, guess what? It's part of the SHA-3 collection of things. So there is official NIST specification for how to use the ketchup sponge to make a hash, to make a MAC, to make a expandable output function, and to make a tuple hash, which is a hash that instead of taking one message, takes n messages and does the nice little domain separation. To be clear, there's nothing special about that. There are 15 different defensible answers, and they're all fine, which is usually what causes problems. Because nobody can agree on one, and everybody feels like they can pick one and be right, and usually they're even right. So the problem becomes interoperability. Like no two protocols use the same one. But tuple hash exists. Nobody uses it because nobody uses SHA-3, and so this might change after the post-quantum because the post-quantum algorithms use SHA-3 inside it, and that's just hard-coded, which, Deo gracias. The old-style cryptography would have said, well, you need a hash, so just plug in whatever hash you have lying around, and then you would have, signature foo with hash with SHA-1, signature foo with SHA-2, signature foo with SHA-3, and that would be a complete mess because I would have to ask you, hey, what signature are we using? Oh, foo. No, you have to also tell me which hash we're using or where. Instead, the post-quantum algorithms said, there's a hash-shaped hole there, SHA-3. Moving on, decided, which means that also you can make test vectors that are always the test vectors because that's the only hash function, which is great. And that hash function is SHA-3. So that will probably lead to an incentive to make that fast and to implementing it in places. Hopefully leads to adoption. But that part, who knows again? It's happening right now. The post-quantum algorithms did not exist as of 2 years ago, as in where they were not specified in their current shape in a way that can be implemented and called with a name until 2 years ago. So yeah, interesting times. Questions?
Are like parameters in SHA-3? Is everything fixed?
That's a very good question. How many things are parameterized in SHA-3? Everything is fixed. Well, there are a few SHA-3 functions where everything is fixed. You can pick between SHA-3 256, SHA-3 384, SHA-3 512, and those are the three sizes, which the only thing they do is they need this thing, and they draw more output or less output at the same time, which is good. That's good design. If you need multiple ones, you bucket them. You say, okay, you use these set of parameters or this set of parameters, this set of parameters. I mean, arguably, you didn't even need that, and we could have just had 128 bits of security everywhere by putting 256 here. But anyway, so yeah, they are fully parameterized. Then you get shake 128 and shake 256, which are the expandable output functions. They're the ones that you can draw however much output you want. And 128 does the actually smart thing of 256 bits of capacity, and 256 has instead 512 bits of capacity, because then the security is the one that they put in the name, which is another smart thing. Then you have KMAC, and I think KMAC is the thing where you put the thing at the beginning, and that's also parameterized at 128 and 256. And then you have C-shake, which kind of takes an arbitrary parameter. Like C-shake is how you make a family of expandable out-of functions by having a parameter which is the purpose of it. And everything C-shake does is shake, but at the beginning, you put the name of the finger domain in there. And actually, KMAC is just done out of C-shake. KMAC is C-shake, where you put in the first, in the initial parameters, the word KMAC, and and then you put the key. So that one is explicitly designed to have an arbitrary space of parameters, so that you can have separate expandable out-of functions for separate purposes, which is very useful because it avoids that problem of the lottery numbers giving out your key. In general, you really want to domain separate the things you use. It just makes your life so much better. And having an actual place to put the domain separator is actually a modern improvement of cryptography, because it used to be that they would just tell you, well, if you need to domain separate, just put a prefix there. And if you forget the prefix the first time around, now you don't have a place to put it, because the message can be confused with the prefix, and now you have a problem. Instead, this way you can, the first time you leave it empty, fine. But then if you change it to an actual value, the context is usually called that parameter that you put at the beginning. It will actually be different from a message that, because an empty context is different from a message with without the concept of context. So yeah, contexts are nice. They put the most signatures in the PQ ones, and I'm very happy about it.
So is the length like R plus C, is it fixed?
Yes, it's the length of your permutation function.
And you just have, so you have one fixed permutation function.
I mean, this is built out of okay. So yes, you
never changes much.
Correct. SHA-3 is made out of Ketchuk 1600, which is the size of the thing, which is nice because it means you can put it in the silicon Ketchuk.
It's 1600.
1600 bits, I think. Yeah. So R plus C is 1600 bits.
So actually, R is much bigger than C.
Correct.
Okay.
Yeah, because otherwise it would take forever to do the thing.
But then isn't it that just doubling the size of C should have made such a difference?
Well,
why is SHA-3 so much?
It doesn't dominate that much. Consider that when you have 512 of capacity, you've left 1,100 approximately of rate. And the difference between 1,100 and 1,300 is a double-digit percentage. And that double-digit percentage goes straight into the double-digit percentage of performance difference, because it's the difference of how many rounds you need to do. But okay, so good thing.
SHA-3 is not like an order of magnitude lower than what it could have been if it was implemented.
Yeah, no, 30%, something like that. Right? A lot of that is bickering, but 30% will sometimes affect people's decisions. Maybe it shouldn't, because 30% of the speed of the hash is not going to show up at all in your high-level benchmarks. A lot of the time, people focus on the micro benchmark and go like, which one is faster? Oh, this one is 30% faster. We made it 30% faster. Aren't we great? And like, how much time were you spending hashing? 2%. 2% times 30% is not much. But different people build different parts of the system. They want their part to be fast. And if you tell them that it's now 30% slower because of no reason, they'll be like, well, I'm just going to use SHA-2.